chi-squared test is a test used to see whether or not two categories are independent or dependent on each other. So for example, I wanted to see whether or not a student's feelings for math is independent or dependent on whether or not they take physics. So in order to do that, I would have to take a survey, and I would have to take a count. I would have to count up the frequency of students who takes physics and loves math, who don't take physics and love math, and so on and so forth. So for example, in this question, or in this table, it shows that 18 students love math and they take physics. And over here we have 19 students who don't like math and they don't take physics. So that's how that data was collected and arranged. Now, the chi-square test, what it will allow us to do is tell whether or not my category, which is in this case feelings for math, and my other category, which in this case whether or not you take physics, are independent or dependent. So the process is somewhat involved, but I'll take you through the whole thing in this video. The first thing that we have to do, or step one, is to create a hypothesis. Oops, step one. Create your hypotheses. So let's go with two hypotheses. So the first one is called the null hypothesis. And the null hypothesis is a hypothesis that states that your two variables are independent of each other. It's a hypothesis that states your two variables are independent of each other. So in this case, whether or not you love math, so feelings for math, is one of my variables, and whether or not you take physics is my other variable. Are independent. So that's my null hypothesis, that the two variables are independent. My alternative hypothesis, oh, I forgot to tell you that this is also called HO. So the null hypothesis, which is HO for short, is that they're independent. My alternative, which is called H1 for short, my alternative hypothesis states that the two things are dependent. On each other. Now, we don't know which hypothesis is true. We're going to do a test to find out which is true. So we just, for now, have to state the hypothesis. We are not yet proving it. We're going to prove it later. So feelings for math and whether or not you take physics are dependent. Lots of writing here, but you can write along, take notes as we're doing this. So, and whether or not you take physics are dependent. So again, please remember that the null will always say that they're independent, and the alternative will always say that they're dependent. And again, we don't know which one of these is true. We're going to now do a lot of math to figure out which one is true. So let's go and let's see how this is going to work. Our next step in this process is to calculate what we call expected frequency. So step 2, calculate expected frequencies. Now, I would like to give you a side note, and this side note is not important for the calculation of chi-squared. It's just a brief explanation of what expected frequencies are and where they come from. Why are these random numbers a part of this process? So they are not so random, and that's the point I'm trying to make. And I just want to share this side note with you so you are aware of where the expected frequencies are coming from. So back when you've done, if you've ever done probability, which I'm sure you have, you probably learned that probability of two independent events, A and B, is going to be equal to the probability of each one multiplied. But this is only true for independent events. Independent events. All right, so this is only true for independent events. So basically what we're going to do is we're going to go through each section and test if it is true, or if it's close to true, or if it's close enough to being true. So if it's close enough to being true, the probability of them both being equal to the probability of each one multiplied, if it's close enough to being true, then we can assume that our events are independent, and that's what we're really trying to test for. So that's the end of the side note. If that was a little over your head because I didn't go into too much details, don't worry about it. But now it's time to come back and completely get everything I'm saying. Okay, so we are going to have to find expected frequencies. In order to find expected frequencies, the calculation is the sum of the row times the total sum, over the total sum times the sum of the column. And this will become clear in just a second what I mean. All right, so first of all, we need sums for each row and each column. So as I'm filling them in, make sure you're using your calculator, make sure you're agreeing with everything I'm adding up here. The sum of 18 and 13 should be 31. The sum of 8 and 14 should be 22. The sum of 5 and 19 should be 24. The sum of all three of those things, so the total sum, let's put a circle around that one because it's super important, is 77. The sum of the first column is 31, and the sum of the second column is 46. Okay, great. Now that we have our sums, we can now start to calculate our expected frequencies. So the first one, let's fill in the first one. So we have 18 as our observed frequency. That's the actual observed number of students who took physics and love math, or takes physics and loves math. In order to figure out the expected value, we have to take the sum of that row, which is 31, and we have to divide it by the total sum, which again we said is 77, and multiply that by the sum of the column, which is 31, also 31. When you calculate that value, you should get 12.48. All right, so let's see that happen again for the following value. Let's erase that so we can see everything clearly. All right, let's do this one. This 13. The sum of that row is 31. The sum of that column is 46. And of course, the total sum is still 77 right there. And when you work that out, you should get 18.52. To make sure we've done it properly, there is a wonderful way to test. The sums should be the same as they were before. So when we add up 12.48 and 18.52, we should get 31, and we do, so we can rest assured that we did that calculation properly. Now I'd like you to go through and try on your own. Pause it and try on your own, and I'll fill in the rest. No, that's incorrect. Let's fix that. 8.86, 9.66. Confirming the sum is actually 31, so it's correct. 13.14, 14.34, and 46 is our sum, so it's correct. All of our sums are correct. They're 22, 24, and the total sum is 77. And that is how we find our expected frequencies. So just so you remember, if our expected frequencies shown here are the same or close to the observed frequencies shown here, then our two categories are independent. As you can see, they're not that close to each other. We have 18 here and we have 12 here. We have 8 here, but that one's kind of close. So some of them are kind of close, some of them are not. So how do we know whether or not they're close enough to say that this is independent, or the values are far apart enough to say they're dependent? Well, that's what the next step is for. Our third step is to calculate chi-squared. What is chi-squared exactly? Well, let's see. That's written that way, by the way. Chi-squared is like a big Greek X. So calculate chi-squared. Chi-squared is a value that tells you how close, again, or observed frequencies are to our expected frequencies. So a small chi-squared value means that these values that I just circled are very close to each other. A small chi-squared value means that these values are very close to these values, which would mean that they're more than likely independent. The love for math and whether or not someone takes physics. But a large chi-squared value would mean that these numbers and these numbers are far apart from each other. And if they're far apart from each other, that would indicate that love for math and whether or not you take physics are dependent because of that whole probability thing I explained earlier. So, how do we figure out chi-squared? There is a formula for that. And the formula is that chi-squared is equal to the sum of FO values minus FE squared over FE. Whenever you see a formula with a summation sign, that's a summation sign. Whenever you see a formula with a summation sign, it makes it much easier to solve it if we use a table. So that's what we're going to do right now. We're going to set up a table, and in our table we're going to list our FO values, or observed frequency values, which are called FO values. We're going to list our expected frequency values, called FE. We're going to make a column for the part in parentheses, FO minus FE. So that's what's in parentheses in our formula. Next, we're going to square those values, because that's what our formula tells us to do. FO minus FE squared. And finally, we're going to take each of those values and divide by each FE value. So here's how this is going to happen. We're going to now have to list all our FO values first. So let's make sure we can see them. So the FO values, we're no longer in need of the sums. We can completely ignore our sums. Our FO values are just the numbers of the people, the frequencies of the people who took the survey. So the 18 people, the 13. Now it doesn't matter what order I list these values as long as I am consistent. So what that means, because I chose to start at right here and go over here, then over here, I have to do the same thing down here. I have to start here, go over here, so on. Alright, so now we have all our FO values listed. Let me line it up so we don't get confused. Now we do the matching FE values, 12.48, 18.52, 8.86, 13.14, 9.66, and finally 14.34. Okay, now that we have that done, we just have to follow what the headings on our table tells us to do. So, FO minus FE, so the 18 minus the 12.848 should give us 5.52. So we could go down the table and fill in the rest of that column, but I find it a lot easier, since that number is in your calculator already, to just square it. And when we square it, we get 30.47. And again, since that number is already in our calculator, we can now take that number and divide by our FE value. So 30.47 divided by 12.48 should give us 2.44. So now we have to go through and do that again. So you're subtracting, it's 13 minus 18.52, and we should get negative 5.52. You square it, you get the same thing that you got before, but now we're dividing by a different FE value. We're dividing that 30.47 by 18.52, and you get 1.65. Now you can pause, feel free to pause, and try it on your own while I fill in the rest of the values. Okay, so you should be checking your work now, and hopefully everything looks the same on your paper as it does on my board. Oh, that's not right. We have negative 4.66 squared would be 21.72, 2.25, 4.66, squared 21.72, divide, we get 1.51. Okay, so now that our tables are all filled in, now we can finish the formula, and this again is the summation sign. It tells us that we're going to have to add up our last column. So when we add up our last column, the value that we get for chi-squared is 7.99. That is our chi-squared value. So you may be wondering, so a few minutes ago we spoke about the fact that if we have a big chi-squared, that means that the numbers are far away, and that means it's probably dependent. And if we have a small chi-squared, the numbers are close together and it's probably independent. But what's big and what's small? That's the question. So that will be our next step. What's big, what's small? Hang in there, we're almost there. So now we're ready for step 4 in this process. And what step 4 is now we can state whether we accept or reject the null hypothesis. And remember, we call that H0 for short. So let's just do that here also. So state whether or not we accept the null hypothesis H0. In order to do that, there is something called the rejection inequality. And what the rejection inequality states is that if the chi-squared that we calculated is bigger than the critical chi-squared value, which we'll discuss in a second, critical chi-squared, also known as K for short. So if chi-squared that we calculated is bigger than K, we can reject the null hypothesis. All right, so we're getting pretty close to the finish line here. Now, what is this critical chi-squared? Well, you can look it up online. If you look in the top left corner, I have a table of values. That's what a critical chi-squared table of values looks like. So it gives a bunch of different critical chi-squared values depending on your particular test. So on the left side, we have something called the degrees of freedom, which is the size of our table, a measure of the size of our table. And on the top, we have something called the significance level, which tells us how accurate or how accurate you want your test to be. So for example, I want my test to be done at the 5% significance level. So at the 5% significance level, there's only a 5% chance that my results for my test would be incorrect. So I will have a 95%, I'll have 95% confidence that my test is accurate at this level. You can go even more accurate. You can do your test at the 2.5 significance level or the 1% significance level. This is really up to you, or perhaps you may be given this as a question and you'd be told the significance level. But I choose 5% for mine. So at the 5% significance level, I am 99% confident. So, sorry, 95% confident. So that's the column I am going to use. And as far as the degrees of freedom, here's how that is calculated. So that's the one I'm going to use. Degrees of freedom, we'll calculate over here. Degrees of freedom equals rows, number of rows minus 1, so I'll just use R, times number of columns minus 1. I have 3 rows, 1, 2, 3, and I have 2 columns, 1 and 2. So my degrees of freedom is 3 minus 1, because that's my number of rows, times 2 minus 1, which will give us 2. Now that you have your degrees of freedom, which is 2, and your significance level, which is, or your confidence level, which is 0.95, we can see where they meet. So degrees of freedom is 2, and it meets the confidence level at this value. So our critical chi-squared value, K, is 5.991. K is 5.991. So now that we have that, we are ready to see whether or not we can accept or reject the null hypothesis. So restating or rejection inequality, if chi-squared calculated, if the calculated chi-squared value, which we got to be 7.99, is bigger than K, or critical chi-squared, which we got to be 5.991, we reject HO. We reject the null hypothesis. Well, since this is in fact true, we do have to reject the null hypothesis. The null hypothesis over here states that whether or not a student takes physics and his or her feelings for math are independent. This statement must be rejected. Therefore, the alternative is true, and whether or not a student takes physics and his feelings toward math are therefore dependent on each other.